So Professor Ahmed is already with us. Good morning, Professor.
Good morning, sir. How are you?
Fine, thank you.
Very good, very good. Where are you now? You are in Casablanca or somewhere else?
No, I am in Portugal.
Okay.
I wish I would be in Egypt, like these pyramids behind me, but unfortunately, it's not possible.
Okay. Yeah, me too. Me too.
Labi, I don't know. Should we begin?
Well, I think we are in that now. It's already 10:05.
Yeah.
If you want to wait 5 minutes more, it's okay for me. Otherwise, we can start. Do you hear me well?
Yes, perfectly.
Perfect.
Okay. And the screen, you see everything.
Yeah.
Yes, we see your presentation.
Yeah.
Good. So let's start if you like.
Yes, I think that we can start. So, good morning to Professor Ahmed and to all participants. I am Sergio Correia, and I will be sharing this session. Today, we will have the talk by Professor Ahmed Ennaoui, entitled Challenge in the Development of Photo-Electromechanical Solar Fuel Technology. Professor Ahmed was born in Morocco. He obtained his master and doctoral thesis in solid-state electronics from the University of Bourgogne in France, and he began his career as associate professor in 79 at the University Mohammed V, and joined the Ham-Meitner Institute in Berlin in 1983 for conducting research for his habilitation. In 87, he obtained his habilitation on the new Earth abundant materials for solar energy conversion. And in 2000, he was appointed head of a research group in the Institute for Heterogeneous Material System in Berlin. He serves as a visiting professor at the Research Center of Solar Energy Chemistry, Osaka University in Japan, and research director at Qatar Environment and Energy Research Institute. He has published mostly papers on the transition metal, conjugate binary and ternary thin solar cells. So, Professor, welcome, and the word is yours. Looking forward for this presentation.
Thank you very much for this presentation. First of all, thank you for inviting me to this very important and interesting conference with very interesting topics. I will first start with the something very introductive, the global warming and carbon footprint and the energy transition. Then I will talk to you about the power to X, learning from the nature. The nature was the first laboratory to produce different compound, different green compound from the solar. So I will talk about it and see how to imitate the nature. I will also talk from material discovery to the market, which is the job of university and industry, and the complexity of this water splitting and power to X. Then I will talk about the evolution of photovoltaics, PV, and photoelectrochemical solar cell, PEC. And then at the end, we will let discussing what we can learn and what we can take away. Okay. So Let's look to the global warming first. As you know, we are facing this problem of global warming, and just after COVID, we can see that there is a rapid growth of solar, of renewable energy. It's about 275 terawatt hour of solar, actually. But the world, what is very bad, very sad, the world still depending on fossil fuel. The global production grow by 3.8 million barrel per day in 2022 compared to 2021. And the global CO2 emission grow by 3 to 1 megaton in 2022. So we have problem. We reach already 36.8 gigaton of carbon emission. So what we have to do? Either we stay in this business as usual, the scenario one, and this is a catastrophe, or we stop now the use of fossil fuel now, so we'll have less carbon dioxide released to the atmosphere. But the best solution is to cut the CO2 emissions, so to develop industry like power to X, for example, to cut this carbon dioxide and to reach something like 34 gigaton of carbon dioxide, which is the mitigation of the different institutions and different countries. You see here this diagram where you can see obviously that oil, coal, and gas are very important. So there is no planet B, as you know, and we have to find solution. Okay. If we look to what the International Renewable Energy Agency have mitigate, the mitigation for in 2050. So we have to make a transition, or to transition away, I prefer this like that, from fossil fuel to watch the Article 6 of the Paris Agreement, which consists of holding the increase, to stop the increase of the global average temperature below 2 degrees Celsius above, and to pursue effort to limit it to 1.5 degrees Celsius. If you look here, you see that there are different possibility: renewable energy 25%, energy efficiency, electrification, hydrogen. And we have also the fossil removal. This means we have to take the CO2 from the atmosphere. And the biomass. So there are different possibility to do this mitigation for 2050, and we have to start to see the result for 2030. And here I just put here different the transport, the building, the power and heat plant, the industry, etc. And we can go for every item here. You can see how much we can gain from we can take out in gigaton of carbon emission. So this is I will go further, and we can discuss this maybe later when we if you like. So let's look to the nature. What is power to X? Power to X is something like to convert the renewable electricity or green electricity into a variety of end product, like hydrogen, like biofuel, ammonia, etc. And I show you here a tree where the tree can take carbon dioxide from the atmosphere and release the oxygen, and can even give us the biomass as food, for example. And they can pump water from the ground. You can see here how the plant are working exactly. And we take the solar, some wavelength from the solar, they convert it to take carbon dioxide from the atmosphere, and they give us some biomass, some food, and even they release the oxygen in the atmosphere. This is a kind of schematic equation where you see that the CO2 and water are taken from respectively from the atmosphere and from the ground. The photon energy are used. We need a catalyst for the plant is called the coenzyme, and we can produce biomass and release oxygen, as you see here. Here we can imitate the nature, and I show you here, for example, semiconductor here, where you can see the valence band, the conduction band. If you make the light from one side, you can see that you can create electron and holes. And if you have another electrode like cathode, you can have hydrogen on the cathode and oxygen on the anode. And this is one very sample possibility to imitate the nature, and this is the proof of concept for this experiment is already known, and there are results. You can see here, by the way, that we start to see the problem. For example, you have to have a certain potential in order to split water into oxygen and hydrogen. The thermodynamic potential, or the theoretical potential thermodynamically, is 1.23, at least 1.23 volt. Okay. So for water decomposition, it's a very important issue. The electroreduction of carbon dioxide also is possible, but you see here all the reaction to fix carbon dioxide are very close to the splitting of water, and therefore you need to find the possibility to separate reaction. This is one of the challenge, because we want to talk about challenge. So you need the light absorption is very important here, the optical band gap, and you need the catalyst, because as you see in this reaction, electrochemical reaction, you involve 4 electrons. And this is very, very important to know. And to get four electrons in one reaction, you need really some problem. You will have some problem of kinetic. Okay. So again, another possibility, instead of using only one semiconductor, you can use 2 semiconducting electrodes. So you have the one N-type semiconductors is a half cell, another one N-type, P-type semiconductor is in the other half cell, and you need really to have some condition like the band gap, and you should also have the catalyst in order to have a very fast reaction. Otherwise, you will maybe have some hydrogen, but you cannot have a very efficient process. And if you want to go to the industry, you need an efficient process. So you have semiconductor here, N-type, electrolyte, and semiconductor here, P-type. And you can see you need also a membrane where you can, when you form in this reaction, when you oxidize water into oxygen and H plus has to go through the membrane, but not the other ion. And therefore, in the other side, you have only the proton will be translated into hydrogen by using the electron. So we will, of course, go back to this kind of problematic. You see here that this kind of configuration with two electrodes, semiconductor N-type, P-type, membrane, etc. It's an imitation, let's say, of the nature. So you have here some issue. Excuse me. The photoelectrochemical PEG use semiconductor electrode material immersed in an electrolyte. That's one point. Solar photon energy is directly converted into chemical energy, hydrogen or other fuel. The potential difference of the two half electrodes is at least or should exceed 1.23 electron volt. That's the thermodynamic potential of the reaction. And the band gap of the semiconductor should be larger than this 1.23 electron volt. And of course, as you see here in this schematic, you should have appropriate position of the valence band and the conduction band of the semiconductor. And that's also very important in order to have the two reaction, one in the electrode N-type and the other one in the P-type. And will be oxygen on one and hydrogen on the other one. So that's how we can, for example, directly imitate the nature and be able to produce hydrogen and oxygen in the future. Of course, this proof of concept here is already exists. I myself worked on this kind of problematic, but it's still under in the lab scale. So let's look now what is already in the industry, the alkaline electrolyzers. As you see the schematic here, you see that an electrolyzer consists of two electrodes. It's not necessarily semiconductor. And on one electrode, you can make the anodic oxidation. This means you will have, because you have alkaline solution, you will have a lot of OH minus, and then you can form oxygen. On the other electrode, the cathode reduction, where the water will be reduced. Reduction is a gain of electron, and you can form hydrogen. And as you see here, the production of hydrogen and the production of oxygen in between, you have thermodynamically 1.23 volt. And there are many reactions for the fixation of CO2 and fabrication of alcohol, ethanol, methanol, etc., and other compound which can be used as fuel. But as you see here, between the oxidation of water and the reduction, between the reduction and oxidation, these two reaction here in red, you have a very critical potential in order to get one reaction here. So the situation and the challenge are very big. I'm talking about electrochemistry, of course. Okay. There is one possibility which is very interesting, is to use the solar energy, solar photovoltaic, and they show you here the IV characteristic. That's the energy you can get directly from solar energy via a photovoltaic panel, for example, as I show you here. And you have the power is the voltage multiplied by the current, what you see here. This energy, you can use it to make the electrolysis of water in an electrolyzer, for example. And you can also couple it with what I show you before, to use a semiconductor electrode. And here, just IV characteristic, which plotted inside the electrolyzer. And you can see here that you can also have the power, and depending of if you have a good catalyst or bad catalyst, you can have more or less energy. You can see, for example, the blue curve, which give you a very small part of energy. And if you have a good catalyst, you can have a large current and a large power, because the catalyst, even if you give 1.23 volt, you have a lot of other problem with the kinetic, and therefore catalysts are very important. If you use the photosynthesis, or the plant use photosynthesis, they have a mechanism with coenzyme to do this. But in the technology, we need catalyst. Okay. There is a complexity for the water splitting and power tweaks. You can see, for example, here, CO2 is the most oxidized form of carbon, and it's extremely stable. CO2. Here, that's the oxidation degree +4, and here for the mono CO +2, and here for formic acid +2, for methanol -2, and methane is -4. And therefore, depending of this oxidation degree, you can have more or less difficulty to reduce the compound. And you see for carbon dioxide is very difficult. So you have a slow electron transfer kinetics. That's one of the problems. That's why we always need a catalyst. The commercial electrolyzer need a lot of current. So 200 milliamps per square centimeter in order to do the electrolysis with 70% efficiency. So therefore, you need a suitable, cost-effective, and stable catalyst. And again, I always show you here this electrochemical diagram where you see the two reactions for water and the fixation of CO2. So there are a lot of possibility to learn about catalyst and about this reaction. And you can see, for example, here the real-time surface science measurement, like X-ray photoelectron spectroscopy and UV photoelectron spectroscopy, to study in real time or in situ the such reaction. This we can do at the Helmut Center Berlin. When I was there, we use synchrotron as well. Okay. Good. So now let's go to the more complicated mechanism. You can see here, for example, if you want to fix CO2, you have to go through different. That's one of the mechanisms, but there are many to transform CO2, for example, in a reactor like methanation into other fuel. Therefore, one has to know the mechanism by studying, for example, the real-time measurement, the surface science measurement, and to know exactly the mechanism, and then to think about which catalyst he can use. There are, here I just show you a very sample experiment with what we call photoelectrochemical cell. Is a glass cell, and you have a working electrode, reference electrode, and carbon electrode, counter electrode, excuse me. And then you can have a IV characteristic, and you can see where is the onset of the hydrogen evolution, the onset of the oxygen evolution, and you can make this kind of study for a master degree or PhD, etc. And there are many ways to make a correlation between the theory, for example, density functional theory, and the calculation and the experiment, and the catalyst what you are you try to use. Okay. So, excuse me. So here is the transition to the low carbon economy. You have the solar spectrum. You can use wind and solar. You can get electricity. You need a smart grid. You need some power electronic in order to get the right current and the right voltage, and also the stability of your electricity from the sun. And then you can inject this into the grid, for example, or you can use the excess for the water electrolysis. Then you produce hydrogen. Then this hydrogen, you can get it through a pipeline, for example, from Morocco to Europe. You can also make the synthesis of new fuel, and I show you how difficult when you compare the potential of the water splitting and the number of electrons you need to fix CO2. So there are a lot of challenge. You can also turn the carbon dioxide from the industry into ammonia, into ethanol, for example, what we call ethanation. You can also use hydrogen, what you produce here from electrolysis through using the solar energy, with nitrogen from the air for the fabrication of fertilizers by producing ammonia synthesis, what we call Haber-Bosch process. So here, for example, is one possibility of transition to low carbon economy, where you can produce hydrogen and you can use this green hydrogen for the production of CH4 or for the production of fertilizers. And that is one of the projects in Morocco, actually. We will discuss this at the end. So you can also use the hydrogen in fuel cell, fuel in car, for example. So in the future, we will have car, train, even aeroplane, where we can use hydrogen. And you need what we call fuel cell. Fuel cell is exactly the opposite of electrolyzers. So you can bring hydrogen, green hydrogen, what you produce by electrolyzer, and oxygen from the air, and together they will combine and produce electron, and therefore you can produce as a byproduct, you produce water. And you see that this kind of fuel cell are under research and development, and even the industry have start to work on it. And there are actually car with fuel cell and working very, very autonomously. Good. There are, of course, a lot of challenge in this topic. Okay. Now, as academic, I would like to show you this schematic here, where we go from material discovery to the market. And I show you here the Mendeleev table of the element, where you have all element. So we can start here by now what we call knowledge development. This means You can, for example, use look which material we can produce as semiconductor, or for solar cell, or for directly converting the solar energy to electricity, etc. And this is the work, the research that we have to do in our universities. Knowledge development, proof of concept from the knowledge development, research and development, technology development, and then of course we should also create a job by a spin-off or a startup. So every university should have a department where we can take the idea from the research and make companies, what we call university spin-off. This exists very much in every country, like Japan, United States, Germany, Korea, North Korea, etc. So this is very important. That's how I see in myself the configuration of the portfolio for research at the university. And you can use simulation and modeling, artificial intelligence, machine and deep learning, combinatorial approach. This means you can make hundreds or thousands of experiments with different conditions to go very fast to gain time before you decide to go in one direction or another. So the material discovery, material science, material synthesis are very important here. Of course, you have to learn, and this is what we have to learn from the beginning at the university, how to read this Mendeleev table in terms of electronic affinity, electronegativity, ionization energy, etc. And to have an intuition that because the affinity electronic of this, for example, lithium, and the affinity electronic of oxygen, we can imagine, we can make it together using all this simulation and modeling, artificial intelligence as raw material to see which product we can get. This is very, very important. Please listen very carefully to this. For professors, they are making research at the university. That's one of the picture what you have to take away from this conference. So from this Mendeleev table, from the fact that one material can absorb a lot of light or less light, etc., or it can be used as for splitting of water, or it is a very stable material against the corrosion, etc., we can think about which material we have to produce. And even you can make a company, a spin-off, only by preparing catalysts, for example, good catalysts. This is the market is very, very big for this kind of business. Okay. And of course, you can see which material is weaker reducing agent and which material is strong reducing agent. For example, for the reduction or the fixation of CO2. Okay. I will go very fast here because otherwise we will not have too much time. Materials. The 3,5 compound are very interesting for the water splitting because these materials are extremely stable. They are extremely efficient. It's very expensive to prepare 3,5 solar cell from 3,5 compound, as you see here, how much material you have to get to make a solar cell. And you can concentrate the light to 2,000 sun and more. And this is very, very interesting topic also. And there is already efficient, very efficient electrode use or combination of cathode and anode using this 3,5 compound with 19% efficiency. This is a project, you can see here the reference, and this is a project done by Hermes Center Berlin and MIT, I think this MIT and California Institute of Technology, and they got this 19%. Thomas Hannabel from Germany, he worked on this, and he was very much involved in conference with us in Morocco. So another way is to go from silicon compound to complex compound. You can see silicon is a very interesting compound. You can dope the N and P, and you can make a good solar cell with high efficiency, but you can go to the 3,5 compound, as I showed you before, and the 2,6 compound. And you can even go further to the ternary and binary and quaternary compound. And this is very interesting to think about for solar cell and for water splitting. And I will not go to the detail here. I just show you here this because it's the topic when I work a lot, at least 20 years on this topic here, where you can see that the symmetry of silicon, when you go from silicon to the quaternary compound, is changing. But the valence stay during the substitution from silicon to binary compound to ternary compound, either in this direction here or with 2,6 to 1,3,6. You have a very the same number of electron, the neighbor of one element here. So this is very interesting. The two way are different. The way here, 3,5 going from silicon to 3,5 compound need a very expensive system. However, for going from silicon to 2,6 compound, you can do it with electrode deposition with a very simple method, and this is very important. And you can, of course, you can control the stoichiometry, the band gap, and the doping. And for silicon, you can control very good the doping because you have to take bore or phosphor. But for this compound like 2,6 compound or 1,3,6 compound, it's just a native defect giving you the N-type or P-type. So, of course, that was my topic where I worked at least 20 years with, for example, copernadium gallium sulfide selenide. And we discovered in my group, for example, a proof of concept for manufacturing using inkjet printing CIJ solar cell. You can find the literature, one article we published with my group, with 11% efficiency. And this is very interesting. This inkjet printing is very important because you can practice what I showed you before regarding this artificial intelligence and material discovery. You can in one ink you can make you can change the compound very easily to formulate the ink, etc. That's why I show you this work here, and it's published in Energy Environment Science, which impact factor more than 30. This means the work is very good. Okay, as I told you, for example, in a droplet of the ink, in a droplet of the ink you formulate. You have to control the stoichiometry, the composition, the solvent, the additive, the adhesion, the viscosity. So it's really, really a very good topic to work on. And I work very much on this area here. Okay, of course you can also develop nanoparticles by hot injection. For example, you can develop nanoparticle, and these nanoparticles can play a role for the reduction, or either for the production of hydrogen and oxygen, and the methanation also. You can try to make catalyst for the methanation, and for Haber-Bosch you can also try to make catalyst for this. So this is a very interesting topic as well. Okay, and of course this is the so we call this the homogeneous catalysis. The other one, what I show you with electrode, is heterogeneous catalysis. I don't know, Chairman, do we have more time? How much time I have, please? Do you
Okay,
want to...
I had no sound. Sorry. Well, we should be ending soon.
Okay. So
That's
good. That's good to tell me this. So I will just escape this part. Anyway, it's not easy. It's not really necessary to. I don't know what's that here. So I will go. I just to show you this this picture here. That you can see here, for example, how silicon technology, the evolution of silicon technology. It starts from the aluminum back surface filled. Then that's the first generation which you find in the market. Then the second generation, where what we call PERC, which is which is the first generation with back surface field, and you can cut with laser the back contact. Then you go to the another generation where all contact, the front contact, is moved to the back contact. So therefore, the front is very free. And then there is the heterojunction solar cell with silicon, amorphous silicon, and N-type silicon, and then the tandem. And actually, the research is on tandem, using heat solar cells, silicon, and the perovskite. And actually, the Helmholtz Center Berlin are already by 32.5% efficiency. So it's beyond the theoretical limit of Shockley-Kaiser. Just this is I don't want to miss this. Now, the key takeaway. What we can, first of all, the Morocco is an ideal country for green transition of the industry. This means we can green hydrogen, we can prepare green hydrogen, methanation, and ammoniac. We're using hydrogen from solar. This means green hydrogen from solar or from wind also. That's one thing. There are a lot of, in 2023, this year, we still have a few days, there is a strategic partnership and memorandum of understanding between Morocco and different countries, like Germany. So there is, I think, Germany, and also the IRESEN is involved in this. to set up an investment project. China also, they come to Morocco with the company. There is a company called China Energy International. And there is a company, Saudi Arabia, Ajlan, I guess, Pros. And a Moroccan, GREA Energy, to develop the green hydrogen project in South Morocco. And the business development consists of to produce 1.4 million tons of green ammonia. Of course, if you want to have green ammonia, you have to have green hydrogen. And therefore, I suppose that green hydrogen will be provided by Morocco, I guess. And this is per year. And of course, green ammonia is very important for fertilizers. And this is so this 1.4 million ton of green ammonia is from 320,000 tons of green hydrogen. I think Portugal also, he has some relation to Morocco for this green hydrogen, but they don't have it here. There is also another project from OCP, the Office Sherifin and Phosphate, I guess the name, and they invest 70 billion dirham in a future green hydrogen ammonia plant in Tarfaya. This is also very important. The business development is to reduce the ammonia import because Morocco bring ammonia from outside. This means we need a lot of money for that. And now we will do it in Morocco. That's very important to know this for young people. They are looking for a job because they have to choose the right study, the right master degree, the right PhD degree, if they want to have a job in the future. Very important. Okay. So another topic for the academic, for professor at the university, is the basic material science in the industry development. I show you in the beginning how I see this in terms of portfolio. And so we need fundamental research on new catalysts, new membrane, gas separation materials, and for more efficient low-cost hydrogen production. We need efficient electrochemical and photochemical decomposition of water for clean and sustainable hydrogen. So we have now for example, electrolyzers. We have to develop new catalysts for the efficient production of hydrogen. And we have to continue to produce photochemical solar cell with one or two semiconductor with very efficient conversion of the solar energy or photon into electrical current. Then there is the carbon capture and storage. I show you before the reaction, how very difficult to make to separate the splitting of water from the reduction of CO2. And therefore, we have to develop method and catalyst and membrane for this. Then, and this is the most important, if you have a proof of concept and you have already a company, startup or spin-off, you have to scale up your product. For example, electrolyzers. Morocco need what we call industry lourde, the heavy industry to make electrolyzer. This is one thing which actually doesn't exist in Morocco. And this has to be done as soon as possible. So if you scale up, for example, 1 megawatt to 20 megawatt, you can reduce the cost by third. This is the from the literature. So we need also technological innovation to improve the performance of solar cell, of the electrolyzer, etc., with new catalyst. Okay. I don't know why. I see. I forget that they have made some. Okay. Now, one point from this COP 2028, I mean 27 is 28 side even. There are open source software for student and for PhD program in Morocco, for example. You can take the data from Morocco and try to see how much your project will be if you use the solar data from Morocco. And this is very important to use this software, which is available either from IRENA or from European Commission. And this I advise students and also PhD program to use this kind of software. Okay. To take away now, I wrote here one slide where I put here 3 kind of electrolyzers, but I don't talk very much about it. Is the alkaline electrolyzer I talked a little bit about. There is also proton exchange membrane, and there is anion exchange membrane. So H+ exchange membrane and anion exchange membrane, OH-, for example. And here are these 3. The first one is already in the industry, but it has to be improved in terms of catalyst and efficiency. The 2 here are less developed, and they have also to be developed. And as you see here, you have many things to develop. For example, the membrane for proton exchange membrane or anion exchange membrane. One has to do some material science to see how the membrane should be. And of course, the development of this solar cell with 2 semiconductor electrodes is very important, and also how to fix CO2 here. If you want to have, for example, this reaction at 0.02 volt versus vacuum, how to manage this in terms of finding the right electrode, the right semiconductor electrode with the valence band, the conduction band well placed here in the energy diagram. This is very important. One possibility, and this is the last slide, I guess, is to use one electrode as a metal electrode and connect to PV panel. This means you can get all this power here, which is the characteristic of the panel, and one electrode as a semiconductor electrode, which convert directly the sunlight into electron and holes. And this kind of solar cell also is very interesting. You can see the detail in this reference here by Wilson in Energy Environment Science. So for one electrode, you have this characteristic IV, which is the characteristic of the module. And for the other electrode, the characteristic is the characteristic of photoelectrochemical solar cell. And there is a way, of course, to measure the efficiency of your system, solar to hydrogen. Okay. So thank you very much for this, for listening to me. And also, I would like to thank my co-worker. I think it's already 10 years. I think 8 years. I'm retired, and I had this group in the Helmholtz Center Berlin where we worked very hard and made a very, very good work. So the floor is now to the chairman, and they will be happy to discuss with you any issue you want. Thank you very much. We don't hear you. We need your micro, I guess. Sergio, we need your micro.
Okay. I'm sorry,
Now.
but the host keeps blocking me, my microphone.
Okay.
And I cannot start it.
Okay,
Sorry.
I'm very sorry.
So thank you very much for this motivating presentation in a subject that should matter to all of us, as you stated in the beginning, for several reasons. I would open now for a few minutes of questions. We have here a question in our in the chat. We have already one. I will read it. So thank you for this presentation. I would like to know how to produce green hydrogen. Prof. PV. I don't know here. The daily energy generated by solar energy, I cannot read, is multiplied by electrolyzer efficiency and then divided by the energy required to produce 1 kilogram of hydrogen. So basically, I think the question is how to produce green hydrogen from solar energy, solar panels.
Okay. So now, as I told you, there are two ways to prepare green hydrogen. One, which is already in the industry hand, which is to use panel and the electricity of the panel, which is coming from the solar, absorbed by the panel, and then translated into current and the voltage. And this current and or the voltage is or the current is injected into the electrolyzer.
Okay.
So there is someone talking in with me. So okay. So now. So someone has to close his microphone. I don't know whom. So the electrolyzer has an efficiency, actually. And when whatever you do, you cannot produce as much as you want, even if your panel is able to do it. For example, let's see that you have a current of, I don't know, maybe more than 200 milliamp per square centimeter. You can just calculate how much electron you have, and you can say for every 4 electron, I have 1 mole of hydrogen, because the reaction needs 4 electrons. So you cannot do it like this by calculation, yes, but not by experiment, and therefore you are limited by the electrolyzer, not by the panel. This means that if you have 100% efficiency of electrolyzer, then it's fine. But we are not, actually, I think it's 70%. The best electrolyzer in the market, I guess. So therefore, you can calculate from the efficiency of the electrolyzer, and you know how much hydrogen you can produce. This is very easy. If you want to have more, then you have to do more research and to get better catalyst in order to have more hydrogen. That's the topic of the research, actually. Everyone is looking for an efficient electrolyzer, more than what it is already in the market. But not only this, you have also to they are catalysts from for example very rare element which are very expensive. Therefore, you have to see the cost of hydrogen and how much hydrogen you produce. And therefore, you have we need much more research. So for the calculation of how much hydrogen, it's very easy. You have just to take your electrolyzer, you see the efficiency of electrolyzer, and you find it. So I hope I answer to the questions of the guy for 1 kilogram of hydrogen. I cannot make if I was in class, we can do this, but not we cannot do it here. So there's any other? So there is another one, I guess. No?
Okay. We have here 2 more questions. I don't know if we can proceed because we have another presentation for this 2-hour slot.
Yeah.
I don't know if the second teacher is already here. Thank you for present.
There's Sergio, we can add more questions.
Okay, so we have here 2 more questions.
Okay.
So the next one, thank you, Professor Ennaoui. Morocco has made significant strides in renewable energy adoption. Electromechanical solar fuels contributing to the diversification of the country's energy mix, and what role can it play in reducing dependence on conventional energy sources?
Okay. So first of all,
basically, there is some difficulty for people to accept this need for transition.
Well, I think for Morocco, the roadmap is clear that by 2030, or if it's not 2030, then it will be 2050, we want 52% capacity in the energy mix. And this 52% or 53% should be renewable. This means also hydro also is included. So therefore, it's very clear, and there are projects now which are signed as a memorandum of understanding, etc., etc. And therefore, I think the part or hydrogen, green hydrogen, will be part of the energy mix. And if you look what they say in the beginning, that this international agency, I don't remember how much this says, but I can go back if you allowed me. I can go back to the here. So if you look to this mitigation by 2050 of the International Renewable Energy Agency, hydrogen is 10% they made. They made hydrogen 10%. You can see it here. So I think, in my opinion, in Morocco, we can reach 10% efficiency depending on the cost. Because if the cost of hydrogen is not going down to be competitive, you cannot imagine that Morocco will produce hydrogen. Even in Europe, they will not buy our hydrogen if it's not if it's too costly. So I think all this project, which consists of producing green hydrogen and translating this into Europe, or using in Morocco, will depend on the cost of this hydrogen we produce. This means it will depend of electrolyzers and the efficiency of the electrolyzers. So
taking this words of yours, the efficiency of the electrolyzer, we have here a question. Could the theoretical efficiency be achieved experimentally?
I think the theoretical you can get if you theoretically if you look to the to catalyst, actually you can get 90% efficiency very easily. But we have to find a good catalyst which can pump electron. That's the question. The electrons are there, and we have to pump it. And this is the rule of the thermodynamically. It's possible. There is no problem. You can with the panels, you can have as much as you want in terms of voltage, but in terms of current, you need to have a good kinetic.
Okay, so I will close with the last question that we have here in the chat. Bubbles are very important for alkaline water electrolyzers. Can the separator porosity affect the bubble formation?
Once again, about the bubble formation.
Can the separator porosity affect the bubble formation?
Can the separator porosity affect? No, I don't think so. I think that you form bubbles of hydrogen on one electrode and the bubble of oxygen on another electrode. Normally, if you work with alkaline electrolyzers, you have the OH minus go through the membrane to the other electrode. Now the questions of if bubble will create a problem on the electrode, I don't think so. Now, if you use photoelectrochemical solar cell, where you have a semiconductor, then bubble is a problem, because your electrode will absorb light. And if you have a lot of bubble on the electrode, then it will be a problem for the absorption of light, in my opinion. And then you need maybe some rotating electrode or something like this in order to avoid this problem. So I don't think the bubble is a problem. And anyway, the problem of bubble will be one of the problem of the industry to sell their electrolyzers, I guess. So they will resolve for sure this problem. But for photoelectrochemical solar cell, which imitate the nature and convert directly light, the bubble is a problem.
Okay.
Because it will avoid the absorption of the light.
So thank you very much. It was a real pleasure to listen to your presentation. I think we can close the session now. Thank you very much for your collaboration.
Thank you. So I will stop the.
We have a second now, but we have another share to continue, I think.
Yes, exactly. The next session will be shared by Mr. Salim. Salim,
I will close my microphone.
Are you hearing me? Salim.
Good morning.
Good morning.
Yes, you hear me? Do you hear me, please?
Perfectly, yes.
Yes. Thank you very much. Shukran. Thank you. Thank you. Yes, if you can start now.
Yes, that's okay.
Yes. Thank you. Thank you very much. Esteemed guests and distinguished colleague. It is with great pleasure, inshallah, and honor that we welcome Professor Haytham Abu Rab to the stage as our keynote speaker for this momentous conference. As you know, Professor Haytham is a renowned expert in the field of energy conversion systems, smart grid, renewable energy system, electric, and power electric converters. Inshallah, we will start with Dr. And Professor Abu this session. Go ahead. Shukran. And thank you for your acceptance to share with us your expertise and your experience with us in this session, Professor. Go ahead.
Thank you, Dr. Salim. Assalamu alaikum, everyone. And it is my pleasure to be with you. It is an honor indeed. And thank you, the organizers, Dr. Muhammad, for the invitation to proceed. So it is about renewable energies, dominated grid, visibility, opportunity, challenges. The outline of my talk will be introducing the topic and then talking about the challenges and possible solutions. Power electronics converters as promising a solution that bring challenges as well. We'll talk a little bit about the grid forming inverters, which is under focus currently. And now having those power electronic systems as active grid players, then I will conclude my talk. So this is our traditional grid structure that all of us know. So it is a unidirectional system in terms of the power flow and communication. It has almost 130 years old and was amazing, the largest humanity engineering invention. And it was performing an excellent way for what was built to. But of course, our time now is different and challenges, requirements, while having the renewable energies that are distributed, fluctuating, and the grid is expanding. So a lot of challenges now appearing, so that transforming this grid into a new paradigm is very essential. Just to talk about this traditional grid, which is based on the synchronous generators, still relatively we have few inverters in comparison with the traditional generation plants that are based on synchronous machines. So this grid, actually, synchronous machines, when we have certain power imbalance, such as demand generation fluctuation or faults, those synchronous generators maintain synchronism and prevent this grid against collapse, against blackout. So when the frequency starts fluctuating, assuming that frequency starts falling because of the kind of imbalance fault, then the synchronous generators, they have the inertia. So those are synchronized with the grid, and their rotational speed starts falling down when the frequency of the grid goes down. So they have kinetic energy, and this kinetic energy is contributing for grid stability. So the synchronous generators, they contribute kinetic energy to the grid. Whenever the frequency goes down, the rotating masses, they deliver the kinetic energy to the grid and deliver immediately, actually, the power while supporting the grid. And this prevents the frequency or the speed of change, rate of change of frequency to be high, and the frequency nadir also to be high, which means that this kinetic energy is acting before the primary frequency controllers of the prime mover starts operating. So those synchronous generators, by nature, they have this kind of this kinetic energy, or the inertia, so-called here, inertia in the grid, that contributes to the grid stability. The issue is different when we have more and more and more renewable energies that are inverter-based. So those have no or low inertia, which means that it is expected that the rate of change of frequency will be very high, and the frequency nadir after the power imbalance appears to be also very high. So this affects other inverters operating that can identify this high ROCOF frequency as a fault in the grid, and then they start tripping, which means that a cascaded failure could appear in this grid. So it is challenging while having more and more renewable energies in the system. But our grid, as we mentioned, is transforming to a dominating renewable energy paradigm, and a lot of roadmaps actually are targeting more than 80% worldwide, more than 80% by 2050. And when we speak about renewable energies, actually those targets are dominating by even not hydro, because the hydro is the increase in the hydro renewable generation is very limited. These places are already taken. So when we speak about traditional renewable energies such as wind or mostly wind and PV systems, which is actually a big challenge. So is this really going to happen or not? And if we see the history and predictions, we can see that yes, this is a true, and it is even faster than what was expected. And we see the increase now in PV installations is yearly over 20% increase. Even here it was 23%, and the wind energy increase yearly is also around 20%. This prediction is almost around 10 years ago, and it was expected that by 2040 we will have 3.3 terawatt of renewable energies, with more than half non-hydro renewable energies. But the reality, of course, roadmaps worldwide targeting dominating grid renewable energies and the high potential and geopolitical aspects actually pushing more and more for renewable energies. And what we see even by 2020, that we have the renewable energies, the traditional fluctuating renewable energies is exceeding the hydro. And now at this time we have more than almost as was predicted to be in the mid of the 30s. So it is the world is pushing very sharply toward dominating renewable energy system. And here are the new installations, and we see that dominant amount of new installations are renewables rather than traditional. So this shows in practice where is the world moving. It is moving and is very fast moving toward dominated grid renewable energies, which means dominated grid power electronics. So those are big opportunities, but those are associated with major challenges. Some challenges like this fluctuating renewable energies. This is a data, and this is hourly variability of renewable energies wind farm from the US. The green is the wind generated energy, and the blue is the load. And we see that those are negatively, most of the time, are negatively correlated. So when we have the load in the peak, we have generation in the valley, and vice versa, which is a big challenge. What to do? Of course, one can see we combine more renewable energies, which is good, but will not solve the problem. Other can say, okay, let us use storage and store the energy when we have excess renewable energies, which is good, but the energy density and the available storage solutions is very, very low comparing with the fossil fuel oil. And when we see that the energy density of 1 per kg of the fossil fuel is 12,000 watt hour per kg, and comparing with the lithium ion, which is very promising, that is available in the market, barely reaching 300 watt hour per kg. So the comparison is very, very, very far away. So it is a supportive, very important, the storage, but cannot solve the issue. So of course, demand management is moving forward in terms of short-term, long-term demand side management, demand response, and shifting the peak and utilizing the energy with proper planning. And of course, you need to have the load smart as well, in addition to have the generation smart. So all those, having those smart are renewable energy based. So you have the generation smart with renewable with power electronics, and you have the storage smart with power electronics. You have the load smart with power electronics. So all the grid now is becoming more and more power electronics dominated. And another opportunity and challenge, of course, is the electric vehicles, and we see that how it is sharply being adopted worldwide. And of course, this is actually a paradigm change that is faster than was expected. And we see from year to year even more than 100% increase in adopting electric vehicles. And dominant amount, of course, we speak about battery electric vehicles. We have plug-in hybrid, but still, of course, you have the batteries. So the charging is an issue in this regard, but a lot of opportunities that those batteries can be utilized to support the grid and to support the load. This the predictions actually based on the data before 2018. And we see it was expected that by 2030 we will have over 20 million units of electric vehicles, and 10 million is almost by 2027. But now we have over the 10 million units available in the market, and all this is associated with lots of charging, and now pushing for the fast charging stations. So the fast charging stations are now being put in this grid, which is a big challenge for For the grid, of course, they can provide lots of opportunities to the whole grid, but also a big challenge. So smart management also is needed. Renewable energy is very important here to support charging those systems, and still breakthrough solutions, innovations, charging, etc., are still needed, and the power electronics is playing a big role in this regard. So power electronics converters, so those are solutions that bring challenges. So now when we speak about renewable energy systems, those renewable energy systems available are operating either in the so-called grid forming or grid feeding modes. So grid forming, the DG system is behaving as a grid forming, which means building the voltage and the frequency, and supposed to behave as a synchronous generator in terms of building the grid. And the grid feeding is just, or grid following, whatever is named. So it's capturing the available renewable energies and injecting and following the need of the grid. Most of available renewable energy systems currently, small and large, are operating in this grid feeding systems, except the very large power plants. So DGs units worldwide are mostly operating in grid feeding. And of course, this is a challenge because those may contribute to the stability aspects and provide a big challenge to the grid. We'll talk about that. So now a lot of push to have the renewable energy systems, big and small, to work in the so-called grid forming. So now a lot of working groups in terms of standardization for that, while we are proceeding to the power electronics dominated grid. Of course, grid supporting, so a combination of building the grid while also supporting the grid in terms of active and reactive power. So this traditional grid that is based on traditional synchronous generators is moving forward to the renewable energy based with less synchronous generator participation. And the future grid will have dominating renewable energies with a much lower number of or portion of synchronous generator-based generation plants. So here we speak about this paradigm that is power electronics dominated, renewable energy dominated, and that brings the challenges in terms of the stability. If we look at the stability comparison between the traditional grid and the renewable energy dominated grid, we see that and it is known actually that demand supply balance in the traditional grid is impacting the frequency in terms of active power. So active power demand supply affecting the frequency, and reactive power demand supply affecting the voltage. However, in the power electronics system, those are linked together. So any imbalance in one of those variables would impact the whole parameters in the system. So the stability aspects is challenging here, more challenging than the traditional grid. Traditional grid is based on heavy comparison, actually, or by analogy to the pendulum network. The traditional grid is represented by heavy pendulums, those synchronous generators with large inertia. And renewable energy system is represented by small pendulums, light pendulums, representing the renewable energy system, which is power electronics based and with low inertia. So if we have a certain disturbance affecting one of those pendulums, such as a fault, it will start oscillating. But because it is heavy, it will return quickly to the equilibrium, to the stable equilibrium, while not much impacting the other system. However, in the power electronics, so those, if we consider the same level of disturbance, the oscillation will be much higher and longer, which means that this system actually is prone to instability in much higher degree than the traditional grid. And now we are proceeding also further into thousands or even millions of those DGs at the edge of the grid, with power electronics based low inertia system, and if those will not be treated in a smart way, then system would be very easy to collapse. But do we need actually to deal with the system exactly as the synchronous generator-based system, our traditional grid? How we need to treat this system? Is our system is really the best that can be, and the new power electronics renewable energy dominated grid should mimic our system? Of course, this is not fully true. But when the synchronous generators are dominating, then yes, those inverter and individual inverters should respond to the need of the system that is dominated by the synchronous generators. Then we speak here about mimicking the behavior of the synchronous generator. So we speak about virtual synchronous generator and etc. But worldwide, actually, it is realized that not fully. We need to be somehow flexible in terms of this new system. We have a new paradigm. We have a new reality. Then, okay, having more renewable energies, rate of change of frequency will be faster, and the frequency nadir will be higher. But those are not faults in the grid. So let us be a little bit relaxed in terms of the codes that are applied in the grid. And this was actually observed by ERCOT. So ERCOT, the utility in Texas, and they were very fast in adopting renewable energies, and particularly wind renewable energies. And they started actually with higher frequency, actually under frequency load shedding, the maximum nadir or minimum nadir frequency, it was 59.5 and more. So, but now they were relaxed in that, and they reduced it to 59.3 because they are putting more and more renewable energies. And in other countries, actually, they started also relaxing the rate of change of frequency. So the blue are that for the traditional grid, their traditional grid. So it is usually below the 1 hertz per second. And now you see in Denmark that now they have dominated the renewable energy grid. It is almost 2.5 because this is the reality. So new codes should be relaxed, but the new codes should be more strict, as we will see. Grid clustering also is a trend now. Clustering in terms of, okay, microgrids, and they create a grid of microgrids, then you will be able better to manage those microgrids and for controllability, stability, and energy sharing, and higher efficiency. And then, okay, go ahead and cluster the grid itself and start to manage it in a clustered way. So this would also help in managing the system when you go for more and more power electronics and fluctuating energy everywhere. Well, this grid is, of course, power electronics dominated, and you have those DGs that now the focus in okay, having those DGs as a grid forming, because feeding, just injecting those renewable energies into the grid while not contributing in building this grid would put the system to faster to lose the stability. So the virtual synchronous generator, virtual synchronous machines is started to be of high focus, because droop control is very traditional, mimicking the behavior of the synchronous generator. Does not need communication, but more or less actually now starting to think about those renewable energies as currently as forming the grid and mimicking the good behavior of the synchronous machines in term. Okay, we don't have rotational inertia, but let us add this as part of our DG in terms of having so-called virtual inertia and virtual damping coefficients, so that the system would start having the inertia and understanding the nature and the need for this grid. Of course, the power electronics and the control, because you have it, it's actually it is of a big advantage here that you can adapt and you can change that by time when you have more and more renewable energies. So those would be smart enough to have those inertias being adapted to the need of the grid, because those are actually part of your control. So this is an example of a DG with a synchronous generator, the same parameters, utilizing the synchronous generator with certain inertia and certain damping, and having this synchronous or virtual synchronous machine, taking the parameters and the behavior of the synchronous generator. Synchronous generator is the red, and the blue one is the virtual synchronous generator, so the DG with the power electronics. But still, when you have the same parameters, it is still faster than the synchronous generator. The good thing that you can, you can make the inertia, you can increase, you can decrease the inertia, and then try to create your need of the inertia in the system. Of course, you increase the inertia, the damping will be lower, but also you can increase the damping constant here, and then try to adjust the need of your grid, which would be in your hand. So those two are controllable. You can have your damping ratio, and you can you have your virtual inertia, and you have your DG behave and go in the same way or better way than the synchronous generator. Because the synchronous generator has its own fixed inertia, there's a fixed damping, and those are set machines, but the power electronics can be adapted now and adaptive to the need of the grid while transforming to more power electronics. Another aspect is of course thinking about, okay, so what grid forming? Do we need to have all the DGs operating in a grid forming? A grid feeding is, of course, is good because you capture the available renewable energy and inject to the grid. And this is the best efficient way. Otherwise, you would lose a lot of energy unless of course you store this extra energy. And we mentioned that storing the energy is too expensive for the big grid. So for a small amount of storage relatively are good to support the grid, but you cannot solve this for the whole generated energy from renewables. So how much grid farming versus grid feeding? We did research on having a certain power electronics dominated grid, and we started having those DGs operating in grid farming and grid feeding. So when you have 100% grid farming, okay, this is the best actually for the grid behavior in terms of stability, behavior, voltage, frequency. So this is the best way, but you are losing renewable energies. And once you start increasing the grid following, of course, the behavior of the system would be worse. And so where is this limit is a challenge. No doubt 50% would be a critical limit for losing the stability, but those should be smart enough to change the operation mode and observe the behavior of the grid so that we would ensure grid stability while utilizing the maximum available power and the renewable energy. So those power electronics systems, they have they are under tough requirements. So those inverters should contribute to grid's voltage and frequency stability. The power electronics converters should make the renewable energy system act like conventional power plant from the point of view of a grid operation in terms of active power, reactive power needs, and voltage and frequency stabilities. Those inverters should work with synchronous generators and with other inverters and should be adapted to the increased number of other inverters while decreasing the amount of traditional generation in the grid. So should be adaptive. Those power electronics converters should provide fault ride-through resiliency. Even now they are intelligent, then they should take care of the cybersecurity and enhance this, not jeopardize the system security. So power electronics converters should enable this renewable energy system to be active grid player. So those should be active grid players and not a burden on the grid. Okay, so power electronics base the renewable energy systems as active grid players. How they can be active grid players? So now grid codes worldwide attempt to make those renewable energy systems provide the ancillary services to the grid and act like conventional power plants from the point of view of the grid operation. So they should provide active power control, reactive power control, frequency and voltage control, steady state operating ranges, fault ride-through. So those renewable energies are becoming indeed active power plants, provide various services and support to the grid. An example of ride-through operation as per IEEE standard 1547, and this is for large power plants, and this is the frequency and the continuous operation, but they should have a ride-through actually at a much lower frequency at specific time. Of course, those are defined under a frequency, over a frequency. So they need to ride through different faults and keep connected to the grid in terms of voltage, in terms of frequency and voltage. And with the voltage is very tough conditions are being imposed to those systems. This is a frequency profile, control profile as per the Danish code. Having those DGs operating either in the so-called reduced production mode or the full production mode, their frequency 50 hertz. And you see, once the frequency of the grid is around 50 hertz, close to the 50 hertz, the DGs that are planned in the reduced production mode, they extract only 50% of their capability. So of course, they should have an intelligence to identify their capability and work only at 50%. Once the frequency of the grid goes beyond this frequency, which means that the grid has more and more load, the generation amount of power injected to the grid should increase until the frequency goes to the 48.7, and then they have the full production, produce a full captured renewable injected to the grid. And the other full production mode should be also adapted to the grid need once the frequency in the grid goes above the 50.15. Voltage ride through is very tough in many of the countries already, and ride through in different countries even goes to the zero. So when the voltage in the grid goes to the zero, they still are supposed to be connected to the grid, and also supporting the grid with the reactive power to build up the voltage in the grid. Even once the voltage goes beyond 50% in the grid, the whole capability of those DGs should be directed to inject reactive power to support the voltage in the grid. So those are already active players, although this is adapted to the high power renewable energy systems, but now is being imposed to the smaller size, and grid forming inverters are coming to be imposed by different standards. Another challenge actually is the fault current contribution. The fault current, this synchronous under fault, the synchronous machine under fault, under like short circuit fault. So the current in the grid goes very, very high, and you give certain time to identify a short circuit and disconnect the load. So what's happening now? The DGs, they contribute to this current. So when the short circuit increases and sharply increases, the synchronous generator has the capability to generate even more 8 times its rated current for short time. So they have very high short circuit current or fault current contributions. Those are amazing, actually, the synchronous machines. Power electronics, we know how those are designed. So when the current increases above, depends how it is designed, above 1.5 or 2 of its rated current, it disconnects very fast. So they don't contribute to the fault current that appears in the grid, which is a big problem for the grid. So it's very important now to think about the fault current contribution in the DGs. Of course, ideas increase the size, the capability of those inverters, and of course controllability and how to contribute to this fault currents in the grid and support the grid. So this is one of the major challenges that is in the new coming and appearing power electronics dominated grid. So stricter codes are very important here. So strict codes for grid support are increasing the cost. So increasing the cost, as we mentioned, with the fault current contribution, even it is for sure will be pushed to have the size of those inverters to be more than 2.5 or even 3 times its rated current, so that can contribute and support the grid. But all those things are associated with the higher cost of your system. Okay, not only the power electronics inverter, but how to operate the system. Certain curtailment. You don't capture. You are not allowed to capture the maximum amount of energy, as there are certain prime contingency you need to support the grid, which means all this is cost. More and more cost for renewable energy generation market. But it is a big support for the grid, which means the grid can be allowed now, can afford integrating more and more. So from one side, you increase the cost of renewable energy systems, but on the other side, you allow for those more renewable energy systems. So those costs are very important to allow for moving toward dominating a renewable energy system. Of course, now more and more with the artificial intelligence supporting the whole system, the whole grid at the device level, at the inverter level, DG level, at the system level. And of course, communicating with the system operators, identifying, predicting, generation, load, and of course having a self-healing nature. Artificial intelligence is now being a lot adapted to build those kind of smart renewable energy systems that can observe themselves and observe the other operating neighboring units, and then creating the even the so-called shield dam concept, so that whenever there is a fault, they can identify, distinguish between a fault and between attack, and they can isolate and observe the status of themselves and neighboring units, and then connect, disconnect, and reconnect when the problem is clear. So it is pushing in this direction, and which makes the power electronic systems now, those renewable energy systems, as active contributor to the grid and the stabilizer to this grid by time. As we see in 1980, the largest PV wind turbine was 50 kilowatt, and it was treated as troublemaker to the grid. So now approaching even 14 megawatt wind turbine, that is active contributor and stabilizer to the grid. And this is because of this power electronics intelligent control and design. Well, it is a comparison. Started scientists comparing between the traditional grid and past renewable energy system and nowadays, and pushing forward to exceed and go beyond the traditional grid, and having a smarter system that has more even capability, more functionalities beyond the traditional grid. And this is doable actually with new technologies and standardization and worldwide vision and clear goals. So renewable energy systems or renewable energy is becoming more suitable to dominate the future grid, of course, thanks to the smart power electronics systems associated, of course, with the codes. So those stricter grid codes requirements are still expected, adopted, and more to come, so that they can keep pushing forward to the renewable energy adoption. Smart power electronics-based generation will allow for functionalities beyond the traditional grid. Of course, those are associated still with many challenges: stability, optimality, scalability, protection, and cybersecurity. And I would like to thank, of course, acknowledge many funds in this regard. Many of those research is performed in our lab at our center, funded by Qatar Foundation, Qatar National Research Fund. Many of my research team contributed. We are organizing a biannual conference in Doha, in Qatar. This is the International Conference on Smart Grid and Renewable Energy, now in January 8 to 10. So very close. We will organize the 4th edition of this conference. So you are most welcome to join us. And thank you. Thank you very much. Any question, please go ahead. Dr. Salim? I don't hear. Dr. Salim, you are muted.
Yes, now it's activated the mic. Thank you very much, Professor Haytham, for your insightful presentation and for sharing your expertise with us today. Really, thank you very much. Okay, we go now to ask question, if any. If someone have questions. Okay, just I have one question, Dr. Haytham. From slide 21, you mentioned about the grid clustering. Okay, it's a good idea, and we use this technique for optimization energy in wireless sensor network, in IoT, etc. Which parameters used to create this clusters with your techniques already used and presented today? Which parameters to choose the clusters?
Actually, Dr. Salim, with the clustering, what we have here, very active research, is the microgrid system. So what we do here is we are creating a grid of microgrid. And now with this grid of microgrid, we are trying to have a certain IEEE bus system. And now having those buses kind of connected to certain microgrid systems. And those microgrid systems would work in the 2 modes: the mode of the grid farming and modes of the grid feeding. And we are using actually certain software such as PSSE, PSCAD, so that we can investigate the operation of a real system. Now, if you go to the whole grid as a grid and you try to cluster it, certain artificial intelligence, some of the students, they are using to cluster the grid as a whole grid in this term. But those clustering the grids really would be used for certain such as more security attacks, identification. So it is about really data-driven thing rather than having those clusters